and also senior manager of TransCanada. And he has over 45 years of experience in all aspects related to not only pipeline, but also research, regulation, design, and development of steam plants, pipelines, offshore structures. And he has, of course, all of us know, extensively worked on pipeline operation and system integrity, including the development of standards and regulations. And as was already mentioned, Dr. Murray was the founding chairman of the SME Pipeline System Division, and also the co-author of this well-known book published by ASME, Pipeline Design and Construction, a Practical Approach, and also Pipeline Integrity Assurance that is used all over. So without any further ado, it's really a pleasure and an honor for me to introduce you, Alan. Please, thanks.
Thank you very much, Luis. I was so quiet here that I got a warning message that my microphone wasn't working. Can you hear me okay?
Yeah, now we hear you.
Well, it's certainly an honor for me. I always remember you fellows, especially now in my prayers, because things are not quite so good in Brazil. So I hope you're staying safe. Shall I try to put this on full screen? Will that work? Let me know if this works for you. Can you see a full screen? Did I lose it?
Yes, now we are seeing full screen, Alan.
Okay. So what I wanted to try to do was give you a quick look at hydraulics in 4 parts. An introduction, then we look at the governing laws and equations for hydraulics. We look at compressible flow for gases, natural gas, and then quickly look at some incompressible flow moving liquids. And then at the end, hopefully we'll certainly have questions, and hopefully I'll have answers for you. So what we plan to do would be, I put numbers at the bottom of each slide so that, and hopefully you got the presentation. So you can make your questions on each question to each slide, and then at the end you can then go back and we'll do that rather than ask questions during the presentation. That's what we agreed, Bruno, right? So people would hold their questions to the end. Is that reasonable?
Yes, that's good, Alan. That's good. Let's do this way.
Okay. Well, now, why do we use pipelines? You know, they're very safe. In fact, they are the safest way of moving hydrocarbons, and they move a lot of stuff, including in Brazil, you move hydrocarbons, but you also use solids. You use slurries, and as we do in Canada, we move copper, we move coal in slurry form. And when it comes to refined hydrocarbon products, we've got over 71 different types of batch products being shipped by pipeline. Very efficient. If you were to take $1, you would be able to move a ton of petroleum by truck, 19 miles, by ship, 200 miles, and by pipelines, 238. So it's the most efficient form of doing that. And I'm going to skip the next 2 slides. Well, this slide you'll see later, showing that the most efficient way of moving hydrocarbons is by oil pipelines in terms of energy density, or by oil tankers. So I'll skip quickly through that. And we'll look at the hydrocarbon types. It's very important that we realize that the very simplest molecule would be methane, CH4. And so as we keep adding carbon and 2 more hydrogen atoms, we increase the complexity of the molecule. We progress from it being an ethane, to propane, to butane, and these we call natural gas liquids. And you have a business in Brazil moving those liquids, and they're used sometimes not so much for burning.
Alan, I'm sorry to interrupt, to apologize for that. I think that we are not, I think that you are not in the first slide anymore, but we are stuck in the first slide.
Oh, how would that be? Is that it?
Maybe your screen, when you share the screen, choose for desktop instead of window. This way it will move on with your presentation.
Nice, help me with that.
When you click, just click on that arrow, arrow in the box.
Now we are seeing.
That's working for you. That's okay now.
Now it's working. Now we are in slide 6 now. Thank
No,
you.
it's
Sorry to interrupt you.
no, that's great. Well, I mentioned that we start off with the very simplest molecule, natural gas, and then as we add complexity to that molecule, adding carbon and hydrogen atoms, we find a couple of things. First of all, the molecule becomes more complex. The specific gravity increases. And so we'll see that for natural gas movement, that's very significant in terms of determining how much flow capacity you can have on a pipeline. So the higher the specific gravity, the lower the volumes you can put through. Now, as you go through these natural gas liquids, the pentane and then pentane plus, that would be C5H12. We start then looking at light oils and then medium oil and then finally heavy oil and bitumen. And that means again that the not only is the specific gravity increasing, but the viscosity is increasing as well. So when we look at natural gas coming out of the ground, we'll find that we've got a lot of methane, of course, which we use for burning, then ethane and propane and butane that's used mostly in petrochemicals. And then there are the other components that we've got to get out of the gas stream, which don't have any energy. That would be nitrogen. And if there's any water present, we want to get rid of that as well, and CO2. And so if you look at the molecular weight of nitrogen at 28 and CO2, which would be 44, they add very significantly to the specific gravity. And that means we are not only transporting non-energy containing components, but it's also limiting the volume of flow that we can have in the pipe. So we want to get rid of those non-energy containing components at the wellhead, or as close to the wellhead as we possibly can. But that means that when we can extract the water, when we can extract liquids, we're left from the raw gas, that is, we're left with what would be called sales gas. So sales gas is about 98% methane, and it would have a calorific value typically of about 36 megajoules per meter cubed. So that's what's normally transported into people's homes for cooking or for heating, and to power stations for generating electrical power. But the remaining gases, the rich gases, the gases that are enriched by having propane and butane and so forth, we would refer to those as wet gas. When you strip off those components, the product becomes lean or dry gas. If you have sulfur present, you would have sour gas, and that's very dangerous because if it were to leak and people breathed it, they could die very quickly. Now, you'll find that it's very interesting when you start drilling for gas, you will find gas if you drill, but you won't find oil. On the other hand, whenever you find oil, you'll always find gas. And that gas is usually in solution, or we would call it associated gas. So if you look at what then happens in terms of our pipeline systems, we've got these wellheads. We use gathering lines, very small diameter lines, to go from the wellhead. And the wellhead, we try to take out as much water as we can. So that's just the possibility of internal corrosion in the gathering system. We take the product to a processing facility, and it's at that processing facility. I tried to draw all these columns here because they're fractionating columns. They're taking out the ethane, the propane, the butane, and so forth. And they will ship those products off separately, usually in another system of pipelines. And we're left then with dry, sweet, natural gas, and that's what goes into the transmission pipeline. So these gathering systems are quite small diameter. Transmission lines are larger diameter, of course, because the volumes have increased. And then we finally take that to the city gate, where we distribute the gas to the end users. And that's a little diagrammatic there of the system. Let's see if I can go to that. Yeah. So I've tried here to show that whether you've got onshore or offshore wells, we have wet gas gathering, go to a processing plant, remove the raw NGLs through fractionators, and that creates this product mix here of butane, isobutane, ethane, propane, sometimes gasoline, and they feed the refineries or the petrochemical industry. And the dry gas is marketable, and it goes into the interstate pipelines. You can look at this diagram later. The only thing that I'd add to it would be that sometimes close to a large city, we will have underground storage, because sometimes the demand for gas switches or changes dramatically during the course of the day, or even through the seasons. In North America, that's true. But rather than design a very large pipeline that may only be fully flowing 2 days out of 365, we designed a smaller pipeline, and we would move when things are quiet, the demand is low, we move the gas into storage and then withdraw the storage for the stored gas at the time when the demand.
Alan, I think that we lost the audio. Alan, sorry to interrupt you. Can you hear me? I think that we lost your audio.
Yeah, he's mute, I guess. Can you unmute him?
No, he's not muted. Alan, can you hear us, Alan? Alan, can you hear me? We are not hearing you. We lost your audio.
Also the video right now.
How's that?
Yeah, now you're back.
Yeah,
Great.
you're back.
Yeah, no, it said I had to switch off, but that's not true anyway. We're back onto the screen again. Is that going to work for you? No?
Yeah, sure.
Yes,
Yeah.
perfect.
Okay. Well, the only thing I was trying to make a point here is that in the offshore, where you produce a lot of gas.
We are not seeing the screen yet. Sorry, Alan. I think that you need to share again, do the same procedure.
Okay, let's see if I can do that. Let's see where I'm going to get that from. Over here. No, there. No?
No, not yet. If you want, I can share my screen and
Yes.
then you present that. That's okay for you?
Okay, we'll try that.
Okay.
We'll try that. That would be good.
Okay.
And then, so I'm on slide 14.
14. You guys are seeing my screen now?
Yeah, yes.
Okay. Alan, if you want, you can click on your screen and you can ask for control. So you can move my screen if you want to point on something.
Where will I? Oh, request control.
Yes.
Yeah, but it's not working. It's not working. It doesn't want to give me control. Don't worry. If you're kind enough to just follow through, we can do that. We'll try that. Can we try? Just use.
That's fine.
Can you see slide 14 now?
Yes, we are all on slide 14. You guys can see my screen.
Yeah, so the important thing about the offshore is that the platforms that are used don't have a very large footprint. So unlike onshore facilities where we've got the facility or the ability to strip out the liquids and have two separate systems, a natural gas system and a liquid system on the platforms, we transport the natural gas plus the liquids in one pipeline. And the only way you can do that is to push the pressure up until the product goes into what's called the dense phase. You'll see that on slide 13. So it means, in fact, that offshore pipelines are much higher pressure than onshore pipelines to allow you to move the product, the combined product, as a dense phase. Now, it also means, of course, that since the production's quite a distance from the shoreline, you can't have intermediate compression. So it's good to have high pressure there to allow for the pressure, the gas as it flows to lose pressure without the liquids dropping out. But when you have it, that's why I've shown two pipelines here, which happens conventionally onshore. And for offshore, we would have the bottom one here that I'm trying to show by. Can you? You'll see here where I've got a single pipeline. That would be typical of what would happen in the offshore. Okay, we could go to slide 15. And there I've got a description of the oil types. Pentanes, we would call those condensates because they're used sometimes to mix with very heavy oil to thin it down, to reduce the viscosity, to make it easier to pump. And we then progress through from conventional to medium oils, and then to conventional oils, and then very heavy oil such as bitumen. Okay, we can go to 16. And are you're still okay? Hello?
Yeah. It's good.
So on slide 16, it's entitled what oil types, what does it mean? Well, you will find that within crude oil, we generally classify it according to where it comes from. So it could be West Texas Intermediate, it could be stuff from Campos Basin, it could be from the Nigerian coastline, where it would be we call it Bonny Light, or it could be from the North Sea, in which case it's referred to as Brent. And then the product from the Middle East is usually Dubai. But those oils actually contain paraffins, which are solid at room temperature, and we would use those for lubricating oil. We could have aromatics in the product stream, and that's used to make benzene, gasoline, and then naphthalene. So you'll find that most crudes contain a proportion of each of those. One thing that's really important is that the older the rocks are in the geological formation, they produce lighter oil. So the rocks that you find in the Middle East, for example, in Saudi Arabia, are very, very old. And so the oil that comes out there is very light. You can put it straight into your engine. Okay, 17. And so in 17, I've tried to show that one way of what we use for demarcating or distinguishing oil types is by its API gravity. And API gravity is very simple. We take the number 141.5, divide it by the specific gravity of our oil, and whatever we get as a number, we subtract from that 131.5. So if you did that for water, which is a specific gravity of 1, then we'd have 141.5 minus 131.5. So the API gravity of water would be 10. And so lighter products like benzene are light oil with a specific gravity of 0.84. If you put that into that equation, you end up with an API gravity of 36. So the higher the API gravity, the more value you get for the oil. And the other thing that happens, of course, is the price of oil is determined by the amount of sulfur that's present there. If you have to spend money to extract it, it costs you money, and so you don't get as much benefit. So that's a little bit of background on the fluid properties of gas and then oil. So we go to 18. Okay. And that's a slide that just said we're going to talk about the governing laws and equations. And there are 4 of those. We'll go to 19. You with me?
Yes.
Okay. So there are four independent variables that we use for defining the state of the fluid, whether it's a gas or a liquid. The pressure, temperature, the flow rate, and the density. And so you need four equations to be able to deal with four variables: the continuity equation, the momentum equation, the energy equation, and the fourth one would be the equation of state. And the first three are all conservation laws. The first one, conservation of mass. So the amount of fluid that goes into a particular element within the pipeline is the same as the amount that comes out. And then sometimes we'll have line pack, we'll have a residual there, and the mass is stored or squeezed with it. Then we have a second, and that's the momentum conservation, which is really Newton's second law, and then energy conservation. And finally, the equation of state. Well, for liquids, we use bulk modulus and the coefficient of thermal expansion to determine that. And for a gas, we use pressure, volume, and temperature. So something like the ideal gas law. So we go to 20. And so the continuity equation is just a representation of mass coming into the pipe. And if you imagine a slice of fluid within the pipe, we're going to say the mass entering is equal to the mass leaving. And the difference sometimes is that we've got line, we'll call it line pack, where the gas is, so there's a residual amount of gas there. Let's go to the next one, which is the momentum equation. And the momentum equation, again, you'll see is made up of, it's really Newton's second law. So these are all the different forces that are acting. For Newton's second law, the change of momentum has to equal the sum of all the forces that are acting on the little fluid element. So the first there, rho for the density times the acceleration dv by dt, that will be an inertial term. And then we've got a kinetic a force due to the kinetic energy. We've got a component there. I'm not sure if you can see it, but rho g delta h is the static pressure. And then the last element there, F rho v squared over 2d, is the frictional, the energy that's contained in the frictional loss in the pipe. So let's go to 22. We go to slide 22. That's the energy equation. And it looks very complicated, but really there are, as you'll see, there are 6 elements in it. The first one, delta temperature by delta small t, is how the temperature in the pipe changes over time. And then the next term is the rate of temperature change. And that comes about because we'll have convective heating inside the pipe volume itself within the fluid element. And then the third element is the change in rate due to expansion or compression of the fluid. For gases, that's called the Joule-Thomson effect. And then the fourth term is the amount of heat. You'll see K there is the conductivity, and that CP is the specific heat. So it's the heat that's flowing either into the pipe or from the pipe into its surroundings. And then the fifth term is the when you've got fluid flow going uphill or downhill, it's doing work against gravity, and sometimes that means the fluid will either heat up if the fluid's going downhill, and it'll cool when the fluid's going uphill. Often not by very much, but nonetheless it's there. And then the very last term is the heating that's due to friction. There's friction between the fluid and the wall of the pipe. And you assume that all the frictional heat is positive or stays with the fluid. Some of it will go into the surrounding soil. So we go to 23. And just a little picture there of heat balance and showing the heat in and the heat out. And the differences will be the the pipe itself can lose heat to its surroundings. And that's sometimes a function of its burial depth. The deeper we bury it, the less heat it loses to its surroundings. And we'll go to 24. And that's just the ground heat the temperature profile. Well, it's defined sometimes by the soil conductivity as well as the amount of heat generated by friction. And we sometimes, within our hydraulic models, we'll have a subroutine that uses the Fourier law to describe how the heat's flowing between the pipe and the ground. And oftentimes, if that, you'll find that not in Brazil, but in, well, it could be in the offshore, you would have insulated pipe, especially when the temperature at the bottom of the ocean is very, very relatively cold, relative to the product. And you'd want to keep the fluid from, you've got a lot of waxy crudes in Brazil, and you don't want the wax to solidify and plug the pipe, so you'd insulate it. You have to do a heat transfer calculation for that. When we measure temperature in a pipeline, we do it at discrete points. We don't measure it continuously along its length. Let's go to 25. And so that's the equation there for the temperature profile along the pipe without any frictional heat. You can look at that later. What it looks like is you'll see that coming out of a compressor station or a pump station where we physically do work, pressurize the fluid, the temperature is high. And then as it goes to the next, progresses downstream toward the next compressor or pump station, the temperature falls. And that's one of the things that's very interesting about the difference between gas and pipelining natural gas and flowing oil. Because as you know, with oil, the warmer it is, the easier it flows. For natural gas, it's the reverse. The warmer the gas would be, the stickier it becomes. And so it's harder to pump. And that's often why in hydraulics for gas, natural gas, down immediately at the pump, as the product comes from the compressor, we put it through coolers to cool it and therefore reduce its viscosity. So it's one of the interesting things about the differences between oil and gas. Go to 27. Not just, we think now about the forces that are acting in the fluid element, the hydrodynamic forces. You've got frictional forces, of course, as I mentioned, rubbing of the fluid against the pipe wall. Gravitational forces, because sometimes you're, especially for liquids, they're very important because the elevation changes. And so you need to be able to measure or quantify how the energy is changing as you go along the length of the pipe. And so you'll find that, generally speaking, we'll find that in gas pipelines, we lose a lot of energy due to friction, and we have to restore that energy to the system by compressing the gas. And there's really two different types of compressor we use. Sometimes with gathering systems, we really are dealing with relatively low flow, but we want to increase the pressure because the reservoir pressure might be low relative to the pressure we need in the pipeline. So you've got to really use a reciprocating compressor. And sometimes, well, reciprocating compressors are more forgiving of the quality of the gas coming in. If you've got liquids present, they can tolerate that. Whereas, centrifugal compressor is used on the transmission side of things, and only after we've gotten rid of all the liquids, because liquid droplets would be destructive to the impellers of a centrifugal compressor. So can we go to 28? And so a little diagram here of just an inclined pipe and a gray element there with the forces that are acting on it. The difference in elevation means there's a difference in pressure between P1 and P2 just through the static head difference. There's a frictional component because of the fluid moving against the pipe. And that work initially, well, a long time ago really, Bernoulli and Leonhard Euler, a lot of history there. Bernoulli's father was very jealous of Daniel Bernoulli, and he didn't want him to take his job in Zurich, so he kicked him out to St. Petersburg, and he joined the royal court of Catherine the Great. But he got homesick, and he wanted to come back to Switzerland, but his father wouldn't let him. And instead what he did was he said, well, I'll send you a companion. And the companion that he sent to Bernoulli was Leonhard Euler. And that was really good because Bernoulli was very, very good at experimental work, and Euler, of course, was very, very good theoretically. So they combined, and between them they produced what you'll find in the next slide, and that is on slide 29. And that's the steady flow energy equation. So that's the Bernoulli equation, really. Now, what's important for gas is, if you see it there on page 29, you'll see a little subscript B. That when we buy and sell gas, when we transport gas, we have, because the pressures, of course, are different in the atmosphere and the pressure in the pipeline at any particular point, we need to use base conditions, and the base conditions are actually 60 degrees Fahrenheit or 15 degrees centigrade, and a pressure of 101.35 kilopascal. So irrespective of what the atmospheric conditions are where you're producing the gas, you always correct them back to the base conditions, and you need to do that in order to make the contracts for natural gas buying and selling so that people are not cheated. If you look at the equation itself, you'll find that you've got a K there, and we'll look at that because it's an important parameter. That takes account of all the unit changes there are. Inside the brackets, the upstream pressure, P1, the downstream pressure, P2, and you'll see that the flow, the pressure is non-linear, fall off in pressure. But what's very important is, can you see the diameter to the power of 5? And then we take the square root of it. So you'll see that the flow rate, QB, is proportional to the diameter of the pipe to the power of 2D to the power of 2.5, D to the power of 2.5. Then what I mentioned earlier on, if you look at the denominator inside the bracket G, G is the specific gravity. So if specific gravity, if the gas gets heavier, then the amount of flow QB reduces. And lastly, we'll look at that little bracket, other bracketed term, 1 over F, the square root of 1 over F, and that's called the transmission factor. That's very important because it tries to take account of all the frictional losses in the system on a gas system. So let's go to the next slide, 30. The Darcy-Weisbach equation, which is very popular, and it's used to help us calculate the pressure drop on a given length of pipe. And so it's proportional to the flow rate squared, and it's inversely proportional, as it said, to the 5th power of the diameter. So you'll see here, 8F rho Q squared over pi squared d to the 5th will be a measure of the how we use the Darcy-Weisbach equation. Let's go to 31. Yeah, pipes are rough. Even when you try to make them smooth, they're still relatively rough. And of course, that means that the rougher they are, the bigger the frictional pressure drop would be. If you look at the fluid flow through when the fluid flow rates are very low, which usually what happens whenever you're starting to produce from a particular basin for the first time, you still haven't built the market for the product, so the flows will be low, and you'll get laminar flow. So laminar flow is consistent with low flows. When you look at when the pipeline is really working flat out, it goes into the turbulent regime. And then in between, we have partially turbulent flow. Ideally for oil pipelines, we like to work in the fully developed turbulent flow regime. And sometimes if that internal, those eddies or whatever you want to call them, the turbulence gets too much, we can sometimes add drag reducing additives. They help to streamline the flow and reduce the pressure drop. So let's go to 32. I made a list there of the different roughness factors between very new, clean steel and steel that has maybe sometimes when we build pipelines, we order the pipe and then it sits around for a year or 2 years outside waiting on the construction to start. And you'll see quite an appreciable difference there in the roughness between new, clean, bare steel and steel that has been exposed to the atmosphere. But let's go to 33. One measure of how much fluid flow we're getting, whether we're going to be in the turbulent or laminar region, is the Reynolds number. And it relates the density, the viscosity, the fluid velocity, and the pipe diameter. And that's sort of a dimensionless number, as you know, rho VD over U. Osborne Reynolds was an Irishman. You know that I'm Irish too, right? But that's for the resemblance ends, because he was very, very clever, whereas I'm far from clever. Okay, so you'll see here that when the Reynolds number, non-dimensional, is less than 2400, we're operating in the laminar flow regime. If we go as high as 4000, then we start and higher, we get into turbulent flow. And somewhere between 2400 and 4000, we're in unstable, partially turbulent flow. 34. So the friction factor, you'll find it's a function of the Reynolds number and the pipe roughness. And so we'll have to look at that on what's called the Moody diagram. The Moody diagram relates the friction factor to the Reynolds number and the relative roughness. So that's in slide 3. Well, we'll see in a second here. I've tried to show here the different flow regimes, the movement from laminar through partially turbulent to fully turbulent. And the important thing here is sometimes that with laminar flow, the whole width of the flow is essentially a boundary layer. And as we progress toward turbulence, the boundary layer comes away from the wall of the pipe. Let's go to 36. And I've mentioned in there about when the sublayers, if you still have a sublayer close to the pipe wall, in other words, the fluid flows virtually stagnant there, the flow is unaffected by the texture of the pipe wall. That gas or liquid coating that sits on the pipe wall effectively means that the rest of the fluid doesn't even know that the pipe's rough. And so you'll find as the flow rate increases, that sublay shrinks, and then eventually we lose it, and then it becomes important to us again just how rough the pipe will be. So let's go to 37. And that's the Moody diagram that you're probably very familiar with. So on the bottom axis, we've got the Reynolds number, and you'll see this straight line. It's the 3 regions, the laminar flow region at the top, they're going from 0 to about 2400. Then we've got the critical zone, which is when we've got turbulent, partially turbulent, and then turbulent flow. And so if you look on the right-hand axis, if you're able to measure, and you can measure in the field, the relative roughness of the pipe and then divide it by the diameter of the pipe, you get that measure of relative roughness, KD. So when you know how rough the pipe is, and you know the speed, you know the viscosity and the density of the fluid, you can compute where you are on that graph and look across, find the friction factor F. And the only thing that you don't have to look at that when you look at you don't have to calculate it at all, because there's a little equation for that straight line for laminar flow. Anyway, another way of plotting that Moody friction diagram is to use the Colebrook correlation, and that's this equation here where the factor in the square root of 1 over f is given you by that expression there, which also, as you see, includes the Reynolds number. And so you'll find that when you're in the laminar region, the friction factor becomes automatically 64 divided by the Reynolds number. And that's where we are there. So those are the governing laws and equations. I was going to move quickly to compressible flow and actually look at how we go about doing some calculations for a gas pipeline. So we go to 40. The things we need to know about gas properties are the specific heat, specific gravity, something called the compressibility effect, because natural gas is not an ideal gas. Air is pretty close to being an ideal gas. So Boyle's law, Charles' law combine to form the ideal gas law, and that works just fine for air. But for the sort of ranges of pressures and temperatures we work at with natural gas hydraulics, we've got to take account of what's called compressibility. And then we'll find there's another phenomenon called the Joule-Thomson effect when we've got throttling of flow, when you've got a movement of when the pressure drops from high pressure to low pressure, there's an associated cooling that goes on, and that's called Joule-Thomson cooling, and it's very important in gas pipelines. And even more so if you were ever going to be involved in transporting carbon dioxide. A lot of people with climate change are thinking of sequestering carbon dioxide and pumping it and pushing it underground. The Joule-Thomson effect's very, very critical there, and you've got to be careful, because if you had a leak in that pipe, the temperature would drop very quickly and you could fracture the whole pipe because the temperatures would drop way below the rest point for the fracture toughness. And then we need to look at the isentropic temperature change exponent, the heating value of the gas itself, how much calorific value it has. And we look at the boundaries of the phase envelope just to make sure that when we're operating, we don't drop the pressure. We have fluid in our system that we don't drop out and have liquids doing damage to our system. And viscosity is very, very important. Now, each of those properties change with the gas composition, and that's why you need to know the gas composition very accurately. And once you know that, you can relate the various properties through either the equation of state, or sometimes you just use ratios or proportion to do that. Let's look at 41, and that tells us the gas composition. You take the reservoir engineer, before you ever design the pipe, the reservoir engineer will give you the gas composition and allow you to calculate the specific gravity, the heating value, the viscosity, and so forth that you need in order to do your calculations. 42. I'm trying to keep my eye on the time here. As I mentioned, the natural gas departs from the ideal gas, and it does so. And we have to take account of that through this quantity Z, the compressibility factor. Typically, the compressibility factor for air would be 1, but the compressibility factor for natural gas is typically in the order of 0.825, 0.925. Let's go to 43. And then we look again at the steady flow energy equation, and you'll see that depending on the flow regime, that factor F is very, very important. 44. There's a whole range of different equations that people have used to try to determine the relationship between the Reynolds number and the transmission factor. The very first were straight lines, the panhandle A, and then the panhandle B. You'll see the angles there are a little bit different. The panhandle A is almost running at 45 degrees. The panhandle B starts at 21 and moves across. Now, neither of those really work. They're two extremes. And so if you took the combination of both of them, you start finding that we've got the type of curve that's in there showing as the AGA turbulent equation and the AGA fully turbulent equation. So the AGA partially turbulent, it's going up, it's increasing from 18 up to about 20.5, and then it remains even at that number as you go into the fully turbulent zone. So people use that equation very often, or they'll use a variation of it, and that's the Coldbrook-White. And that's the curve. Instead of having the transition point, like two straight lines and a point where they intersect, we use the Coldbrook-White. But there were a lot of tests done on the gas system in Texas, and that's where those points are that you'll see the dot that are around the AGA, fully turbulent, partially turbulent. So people use those, and they're critical because if you use the wrong value of the transmission factor, you can over-design your pipe, and that means it'll cost you a lot more money than you really need. So 45. It's just 45 is just a whole list of you'll see they're very, very common. Just the constants are different, really, but the format of the different types of equation, the rough pipe law, the Weymouth law, the AGA, they're all much the same in their format, and people sometimes will use one or other of these to, depending on, they'll go to their own pipeline, they'll carry out tests. They'll find out how their pipeline is best described, which of these equations best describes in practice what's happening with their system. Go to 46. And you'll find that, as I mentioned before, the flow rate varies with the diameter to the 2.5. So if you wanted to increase the amount of flow rate, you would increase the diameter. So let's go to 47. And what I did there was I've taken 6 different ratios of pipe size, nominal pipe size of 20 inch divided by the nominal pipe size of 16 inches, the ratio of the diameters would be 1.25. But when you raise that to the power of 2.5, you find that just increasing the pipe from 16 inches diameter to 20 inches, you're increasing the flow by 70%. You can see that you go to 1.7. Now, if you buy a bigger pipe, or it'll be 20 inches rather than 16, so there's more steel. You'll have to make a bigger hole, a bigger ditch. So if you look at the ratio of the costs, and that's what the fourth column there is, you see that you get a benefit of 70% increase in flow, but it costs you 26% more. But that's still a good deal. And then as you look down the rest of that table, you'll see that the deal's not quite as good when you get 48 inches compared to 42. You have a 37% increase in flow, but the cost is a 22% increase. Anyway, what this tells you is oftentimes we find in North America it's getting more and more difficult to get permission to build a pipeline. So if you can, it's in your best interest to make the pipe as big as you possibly can, especially when you're crossing rivers or going through very sensitive areas where it's going to be exceptionally difficult to get permission. Build the pipe through there at the biggest diameter that you possibly can get, so that you can expand your system later without having to go back and twin that pipe. Okay, so 48. And I mentioned before about the soil temperature and how important it was. And it means really that the higher the soil temperature, the lower the rate of heat transfer from the gas, because the gas is usually at a higher temperature than the ground. And so as you change the temperature of the gas, you're improving its viscosity, so you get more flow through there. We talked about that before. Let's go to the next slide. So when you look at pipeline capacity, that's the throughput. It's a function of pipe diameter. You saw from the steady flow energy equation, it's a function of the operating pressure. And it also for gas is a function of the operating temperature. When you want to increase the capacity of a pipeline, usually what happens is that you do that by adding compression. When you're adding more flow and the same diameter pipe, the friction losses will go up, the pressure will fall, and you need to restore that pressure, so you can put in another compressor station to do that. And that's usually the cheapest option. The second option, when the flows are really increasing, is to twin the pipe. And you can do that with natural gas because the fluid itself is always the same, no matter where it's coming from. It's treated as it comes out of the different processing plants. It's 98% methane. And so that means you can have parallel pipe. They can interchange with each other. The fluid can mix, and it's all the same product. So it's very easy to loop and increase capacity by looping on natural gas. Let's go to 50. And you'll see here, I've drawn just a little calculator I have at home here for calculating the effect of increasing flow rates. I've gone from a flow rate of 270, these are imperial units, 270 million cubic feet a day, and increasing, it's the same diameter pipe, it's the same length of system, but going from a flow rate of 270 to 310, upstream I start off coming out of the one compressor at 870 pounds per square inch, and when I look at the downstream pressure, it has fallen to 793. So the very top example here shows that I'm moving 270 million cubic feet through a pipe that's 27.2 inches internal diameter over a distance of 67 miles, and the delta P is from the pressure drops from 870 down to 793. Now you need to bring that back up to 870 again, so you have to have a discharge pressure here of, it looks like 1,000 pounds. So you need 2,700 horsepower to do that, and you need to calculate the amount of fuel you need to burn in that, because that's going to be an operating cost. And you'll find the compression ratio going from 793 to 1,000 is 1.26. We'll find that typically compression ratios are optimally about 1.3. So every time you increase the pressure of the compressor station, you want to be no greater than 1.3, where you start getting inefficient. Now, if you go to the second example below, increasing the flow from 270 to 310 or flow, so the pressure drops. It's further. It's not 793 anymore. It's 767 at the downstream, and that means that pushing that back up to 1,000 pounds per square inch, you've got to have more horsepower. You need a bigger motor. You've got to go from 2,700 to 3,100. So it costs you more capital, and it'll burn more fuel, and you need to be aware of that too. So let's go to the next slide. That's what people do when they're doing their calculations of trying to optimize on the type of facilities that they would have or need. Now, they do that by developing what are called J curves. And it really doesn't matter whether you're building a gas pipeline, a liquids pipeline, or even a road system. When people are building roads, they want to know how many lanes of traffic to have. If they made a 12-lane highway and only 4 lanes were occupied, people would wonder, who did that and spent all that money. On the other hand, if they built a 4-lane and it was crowded every day, they'd wonder, well, why didn't they build 6 lanes or 8 lanes? So what we do with the J curve is try to increase the amount of, pick a system with a pipe diameter, compressors located along it. We increase the flow, then we calculate the pressure drops and whether we need a new station and how much it's going to cost. And we end up coming up with curves like this. And what we really want is a nice flat curve. That means that, because the ordinate on the left-hand side is the cost of moving 1 million cubic feet of gas or whatever the unit volume would be. So we really want to have the capacity of keeping our costs low over a very wide range. And so you like those curves to be as flat as could be. So the choice that you would have there would be, you would look at the whole, I've used 3 here, but you would use maybe 30 or 40 examples as you did this. And number 2 was operating a pipe at 12,400 kilopascal, and that was the optimal for you. So we use these J curves to come up with the optimal diameter and spacing and power on our system. So that's our that's what we're going to look at for natural gas. And I'll move quickly to the next slide, which is 52, and look at incompressible flow. And then we go to 53. 53 is just a picture of a little diagram of different production areas with again, gathering systems, bringing their product into some form of refinery where it's refined or treated, and then eventually it's pushed across the country in a larger diameter transmission line. So 54 is a little diagram of how the value chain, as we would call it, works for liquid hydrocarbons. The left-hand column, left-hand side of the slide, is where the oil comes from. It'll come ashore, or it'll be produced onshore, and it'll go to a tank. It's taken out of the tanks and pumped to a refinery where it's broken down into different products, and those products are separately stored, and then they're moved across the country, either in single pipelines, which would be very inefficient. If you had 71 different product types, you're not going to build 71 pipelines. So they're going to be batched. We'll call that batch production, and move more than one product in the same pipe. Take it to the heavy users first, the manufacturers, because their demand for energy is greater. And eventually it will go to your home or your local gas station. We can go to 55. Go to 55. An equation of state for liquids. We find there the American Petroleum Institute and ARCO at Atlantic Richfield produced a bunch of equations that people use to describe the equation of state for liquids in terms of the bulk modulus, the temperature, the thermal expansion coefficient. And they're a function, as I say, of the pressure and temperature. And those equations are when we do our hydraulic calculations, they're embodied in the equations. So let's look at a little diagrammatic on 56 of the Darcy equation, the Darcy-Weisbach equation. So the frictional head loss is F, the friction coefficient, times L, the length of the pipe, times the velocity squared of the fluid flow divided by the diameter times 2g. So you'll see just that. I've tried to put out the different elements there, the 5 components, that show friction factor, length of pipe, acceleration due to gravity, the internal diameter, and the fluid flow. We'll go to 57, and you'll see again that for liquids pipelines, we're moving in either the laminar regime or the turbulent regime. We've got to be very, very careful when we batch pipelines. If we go too slow, and we'll find that there's a possibility that the fluids, the heavier fluid, can push through to the fluid in front, and you'll get contamination. So we've got to be very careful then. We like to work in the fully turbulent regime. So let's go to 58. I'm keeping my eye on the time here. So when we're doing a hydraulic design, what we really need for a liquids pipeline is to figure out what are the total pressure requirements. You need to be able to overcome the frictional losses. You have elevation changes, which are very important. They're unimportant for a gas pipeline because the density is so low. But for a liquids pipeline, you've got to be very wary about the static pressure change due to elevation. And we try to figure out what's the optimum pipe size, what pipe grade we would use, the type of steel grade that is, and that will tell us the diameter. The grade will tell us what wall thickness we'll need for the safe transport of the pipe, and then we figure out what the friction factor would be from the surface roughness. We also do a calculation for the power that we need, and we don't have time to do it here, but there are equations we use for calculating pumping power. And we do a whole, just like we did with gas, looking at a variety of alternatives. We build J-curves, and we try to find out what is the best feasible alternative of the very many options that we look at. Try to find out what the annual average energy cost will be and what our capitalized cost would be, and then do that over the life of the pipe. And we end up by knowing how much to charge our customers by taking all of those costs and then using a net present value calculation to bring the costs back to today, and then divide that cost by the volume we're shipping today, and that's how we know how much to charge per meter cube per kilometer that we move. Now, the next calculation, next slide actually, which is 59, that's our total pressure requirement. We add up the frictional pressure drop, static pressure change. We've got bends and losses through valves and so forth. And so we need to include those in our calculations. Static pressure, of course, is due to the elevation change and the density. So that's only important when we've got hilly areas. We don't bother with it when the countryside's flat. The delivery pressure, in other words, the pressure at the end point of the pipeline, is determined by whatever the terminal requirements are, whether you've got tanks or however you're going to store the product, and also the elevation at that point. 60. We need to be aware that between the pump station and the next pump station, or a pump station and the delivery point, will be a hydraulic pressure gradient. So that's a graphical representation of how the pressure's changing, usually pressure drop going along the pipeline. And we're going to superimpose that gradient curve on top of the pipeline elevation, and you'll see why in a minute. That's look at 61. So in most of our pipelines, long distance, going through the losses that we have in bends, the losses that we have going through the valves are very, very small compared to the frictional losses. It's only when we get into pump stations somewhere we've got lots of bends and we've got lots of components that we start thinking about the pressure losses there through valves and fittings and so forth. So the minor losses we can calculate just by looking at that. The delta P, the pressure loss, is a pressure loss coefficient K times rho V squared over 2. You get K from looking up in some of the catalogs. A crane catalog has got different coefficients there for different types of equipment. Let's look at 62. So when we look at, it's very important that we don't plot pressure when we deal with head, and so we convert pressure to velocity head. And so V squared over 2G is called the velocity head. And when we look at the actual pressure in the pipeline, if we divide that by the density of the fluid times gravity, it'll be the pressure head. And that allows us actually to do a plot that we find on 63. So 63 shows you that as you move from a pump station out a distance of 80 kilometers to the second pump station, we may have gone up. The elevation has changed, obviously, as you see there, from 1,500 meters up to around 1,650. And there'll be a change in the static pressure for sure. So what you need to be aware of is what happens on 64. And that is, we need to be sure that we've got enough pressure at the discharge of the pump so that when we take account of the frictional losses, that the pressure at any point in the pipeline is the head that's at any point in the pipeline is greater than the elevation. And you'll see why on the next slide. If you were to plot the elevation, and if you were to find that the energy intersected, in other words, the ideal here is that the hydraulic grade line or the energy grade line should be well above the elevation, the highest point. Because if it's not, we'd have negative pressure. And negative pressure is really bad news. It means we can't pump at all, okay? So you be aware of that. You always have to have enough pressure to get over the high points. And we've got to be careful with some of the products that we ship because there are high vapor pressure liquids. Those are fluids who have a vapor pressure that at 38 degrees C have a vapor pressure about 1.4 megapascal. So that they would be liquefied petroleum gases, ethane, and the very light hydrocarbons. And you've got to be very careful with those because you can get two-phase flow. In other words, if the pressure drops, you'll get a gaseous phase and you'll also get liquids. And the separation of gas and liquids is dangerous. And you'll see when we go down to, well, the reason for that is because when the pressure in the fluid drops below the vapor pressure, the liquid starts to boil. And that's a condition called cavitation. Or it could also be something called slack flow. And you'll see that in the next slide. But where you get this two-phase flow, it's more likely to happen near the summit of a mountain where on a very high point on your pipeline system. And it can do very serious damage to the interior of the pipe. It can even make the pipe collapse, actually. So we'll talk a little bit about what we do to mitigate that in the next slide. So if you go to the next slide, 68, you can see here that this is a pipeline that's going up over the top of a hill. And it means in actual fact that the velocity going up, gravity is slowing it, pulling it back. On the other side, if the pipe is the same diameter, gravity is accelerating, so the velocity going down is greater than the velocity going up. And so that means there's an imbalance in the fluid, and you can develop a vapor pocket. Now, if that vapor pocket actually ended up filling the pipe, you could see that you're separating the liquid flow into two different columns. That's called column separation. That's very dangerous. Your SCADA systems will never work in this circumstance. So you've got to be very, very careful when you're in hill country and you're looking for SCADA. You better be careful. And so how we counteract that is we put a valve on the downstream side, on the right-hand side of that curve, and we partially close the valve. And what we're doing is we're increasing the back pressure. We're forcing the fluid it naturally wants to go at VD because the gravity is accelerating it, but we slow it down, and then we don't get the vapor pocket forming. And that's how, because that vapor pocket could also result in the pipe collapsing, and that would be really dangerous for us. You've also got to be careful of this when you're doing hydrostatic testing, by the way, because if you get your water source from a river and there's a lot of air in it, then the air can form a pocket like that, and you'll never you actually have to drill into the pipe locally to get the to draw off the air. You'd never get the pipe emptied of water. 69. So I mentioned before that we've got many products, and we're trying to move them all in the pipe. And rather than build a dedicated, well, if we've only got a single pipe product, we would build a dedicated pipeline. But multiple products are batched and they go into the same line. And what we try to do is put together batches of fluids that have very similar fluid properties, similar density, similar viscosity, so that we can keep flow even. The speed of flow is going to be in the pipe is going to be determined by the thicker fluid, the fluid that's most viscous, and so you've got to be careful about that. So let's have a look at how we can batch the pipe and still maintain integrity of the product. And so if you go to slide 70, you'll see here what I've tried to show is diesel fuel followed by regular gasoline and then premium gasoline. Now, there's a value associated with each of those. If you owned those products and you had them being transported by a company, you wouldn't want to have your regular gasoline compromised by diesel. And so what we do is we separate those. Now, you can physically separate them by putting a pig in there between the different faces, different batches, but then you'd have to get the pig out. It's a mess. So what people do these days is they use synthetic fuel, synthetic oil as a buffer. They'll call it transmix or a buffer. Now, you can see that, I mean, there's no pipeline that's horizontal like that. Most pipelines are going to go up and down and around corners, and so there could be mixing. So there will be some mixing, but it would be, instead of the gasoline going into the diesel fuel, it would be gasoline going into the transmix. And so we'll find that when we get to the end point, we separate out the transmix. And so we haven't degraded our regular or diesel fuel or even aviation spirit. It's the transmix that absorbs that. And so what we try to do to minimize this is have batches that are quite large. We try to make the batch size quite large. We'll go to 71. We're almost there. Let's go to 71. And so again, I tried to show that the interface and the buffer, and it's very important for us to track where that is. And so we have hydraulic models, mathematical models that are going to try to predict where the different interfaces will be. But when it gets to the tank farm, we know that the densities of these fuels are different. So if we have a sound meter, we can put a sound wave into the wall of the pipe and pick it up on the other side. And so we can use that, the speed of sound and the different liquids, to tell us where the different, whether we've got gasoline or LPG or diesel. And we usually locate that upstream sufficiently to give us enough time to open the valve, so that we strip off the gasoline and put it into a tank containing gasoline. We close another open another valve, and the pipeline discharges diesel into a tank for diesel. So it's only if you would use sound as the basis for doing that. If the densities are very similar, then sound will not be able to effective. You won't be able to do that. So then what we do is we rely on color. So you'll put a colorant in the batch interface and use an optical reader. So you've got a little spyglass, and so as you come close to the tank farm, you see a change in color, and you know then the next batch is arriving. So 72. Interfacial mixing, you've got to be careful about that mixing at the boundaries, because as I said, one of the products to cut into the next product, and that will compromise the fluid, and you won't get full value for your money. So 73 shows you that product A and product B, there's an area in between there where we do get mixing, and so that mixing hopefully takes place in this transmix, and it's degraded. That's usually sold off, by the way, to people who would burn that in a furnace. It's slop. We would call it in English slop, S-L-O-P, slop tanks. And it's got value because it's still got calorific value. It can still be used. So 74. When we look at injections and deliveries, the very important thing to realize about batch pipelines is you can't loop them, because you would never be able, if you had parallel lines, you would never know that when you join them together that the same product would be shared. So we've got to be very careful about taking product the right, no mixing of a product, and taking product off at the right point. And so it means then that we always have to be sure that at different points we can have what's called side stream injection. We can have or full stream injection. Full stream injection would be, suppose you've got some gasoline and you also want to put more gasoline in at a particular point, and they're both compatible, then you can introduce one into the stream. You can have an injection of that new fluid in there, and it won't be a problem. But if you've got a totally different product, then you have to stop the pipe, hold everything up that's coming down the pipe in order to introduce this new fluid coming in as a side stream. And where that causes you to think is that stopping and starting causes a big pressure cycle on the pipe, and it can lead to fatigue, and it has an issue for operations, for integrity, where you might end up with fatigue cracking. And so you have to be careful about how you handle the batches. Let's look at the pipe branches again. If you've got branches coming into your pipe or going off the system, you can introduce, if you're going to be bringing fluid in from somewhere into your pipeline, obviously the pressure has to be higher in the branch line than it is in the pipe, or it won't be able to put product in there. And so that means we normally have a pump located at what we call the flow lifting point, so we can raise the pressure to be able to push the fluid into the transmission line. How do we control that? Well, you control the fluid flow from a control center. It's continuously measuring pressure and temperature at compressor stations, pump stations. It'd be looking at vibration levels. It would be checking on the volumes, the height, capacity of tanks, so that you know whether the tank's full and whether you can put more fluid in there or not. It also looks at the status of the valves along the length of the system to make sure that they're open or closed. That's how you exercise control. Now, that would be, you should ask Mike Yoon to give you a little chat about how automatic control works, and I'm sure he'd be delighted to do that. But supervisory control and data acquisition, you acquire the data from remote terminal units along the length of the pipe or at pump stations, compressor stations. And when you get that, then these fellows in the control center, they exercise supervisory control. It's also possible for you to have what are called programmable logic controllers at the pump station. We have local control, but we'll get Mike to get you about that. So let's look at 77. We set operating limits for safety reasons. It means that sometimes we'll set a particular pressure value at the suction side of a pump. We don't want it to fall too low, or we'll get cavitation. We set a pressure restriction on the discharge side of a pump so that we don't damage the pipe. And we'll have different pressures set at different points along the system to protect the terminal equipment. Sometimes set the discharge temperature as well for heavy crude, but that's another story. And because we have to pay for electrical power to drive the pumps, usually in most countries, the electrical power is cheaper at night. So if you've got a choice, you try to move more product at night than during the day. And so it's cheaper for you to do that. If you do have a problem with, say, overpressure, sometimes you might find the pipeline might surge. Then you can have bursting discs. Although if they burst, they're a bit of a pain to try to replace them. So what people are inclined to do now is they use what are called surge chambers, and so they're surge tanks. So as the pressure would increase, suppose a valve were to close suddenly downstream, or a pump was to come off, maybe a lightning storm or something cut off power, and the pump could no longer pump, you would get a pressure wave going up, and it would increase the pressure. Well, when it would get to a point like what one of these surge tanks would be, there's a piston in there and it's preset. So there's gas, you control the pressure of the top. And so as the liquid, because the liquid is incompressible, it doesn't have to move very far for the pressure to fall dramatically. And so these are relatively small devices there. So the very last slide I had really is just something which we talked about the other day with Bruno and France, and that is maybe where the business is going in Brazil, and that would be where you've got more than one operator wanting to move product onto a particular pipeline. And so we would call those shippers, rather, multiple shippers, people who, many different people who own the product, but there's only one pipeline, and they're not going to build their own pipeline. They're going to ship it on your pipeline. So they have to have a contract, and they have to nominate to that contract how much they're wanting to ship in a particular period. So they make a transportation request. You go down the left-hand side there, then they call that into the pipeline operating company. They validate that you've got a valid contract, confirm your nomination. Yes, you can move 20,000 barrels or whatever it is on a particular week. And then that goes into the batch schedule. And then what you're going to have to do is measure where it comes onto the pipe, where it goes off the pipe, because you charge them for it based on the volumes that they've shipped and the distances that they've shipped. So that's what we go. We look at the right-hand side there, and we get what's called volume accounting, and that we keep track of the inventory, because when people entrust us as the pipeline operator with their product, they want to know that they put in 20,000 barrels and they want to get out 20,000 barrels. So we have to maintain control of that, and then we invoice them. So that's how you run the business, and that's where you're headed actually in the next 5 or 10 years in Brazil, as you open up your economy to different people. So that's what I had for you, very, very high level, and I'm sorry that I had to rush it, but I hope it was of some sense to you. So our last slide, I think, is the next one, is 81. You have
on my apologize for that. I don't have the 81 here with me.
81 is just this one. It's the presentation outline. It's the end. It just says obrigado.
Yeah, this one. You do have it.
So we have arrived. We have arrived at the end. And if you're still awake and you want to ask questions, I'm sorry that I rushed it so much, but we tried to cover a lot of things. So ask questions. What's the best way for them to do that? Bruno, will you take their questions and then pass them on, or what do you want to do?
Alan, first, thank you very much for the presentation. Okay, again, we'd like to thank you for that. And normally we're opening for all the guests to do their questions. So guys in the audience, please feel free to ask your questions to Alan directly, okay?
Hi, Alan. This is Luis here. Thanks for the presentation. Are you hearing me? Yes?
Oh, I can hear you, Luis. Thanks.
Yes. Thanks for the presentation. I'd like to hear your thoughts on what is the future for lowering the friction on pipelines in terms of newer materials, not drag reduction, but on the surface itself. You see a lot of investment in high-grade steel for structural reasons, but not for lowering drag. Is there any initiative in this?
Actually, two The first would be to coat the inside of the pipe. As you know, you could do internal coating, but it degrades after about 5 or 6 years. So it only gives you a certain amount of time, and it only is economic if you use, say, pipe of about 0.9 meters diameter and above. You don't get the benefit of internal coating when the pipe diameters are small. The second thing that they've done quite a bit of research actually in Nova or TransCanada is, how a shark, if you look at a shark's skin, it has what are riblets. Riblets. And if it's possible, now we've only done that in small sections actually to see if it would work. But Kamal Bartras did a lot of work using riblets, and that has a lot of potential. I mean, if you could, it's creating small undulations on the inside of the pipe. So you have to find out how you can do it on a small pipe. You have to how to do it extensive on a pipe. That would be the future. Do that. It's the friction losses both on the gas pipeline and liquids pipeline. So riblets.
Yeah, riblets. Right. Yeah, I see.
Yeah.
Your voice was cutting a little bit. It works either way for gas or liquid, or
yes, it would. The work that Kamal did here with gas, though, but it works on both. And but in a in a laboratory type setting, though, and very small full scale, they're only maybe about a joint about 12 meters. So it would take a bit of work to get it to be fully operational, but I think it has promise. Now, what happens is that a lot of people would use drag reducing additives instead.
I see. It's much higher reduction.
Well, it can be, but it's very expensive. And what happens is, that they're long chain, they're long chain molecules, so they're like threads, like cotton thread. And when they introduce them into the pipe, it's almost like having white lines on the road so that cars can stay within the white lines. Those eddies are going to stay within the white lines, so they don't interact, so the energy loss in the pipe is reduced. But when you get to a pump, blades and the pumps cut the threads, and so after a period of time, you've got to reintroduce more additive, and it's expensive. Now, that's an operating cost. So what people have to do is trade off whether they want to spend a lot of money on reducing the drag, or whether they just be better off accepting that the pressure losses will be high and put in a bigger pump. Now, putting in a bigger pump is a capital cost. So they trade off the capital cost versus the operating. If you put those riblets in, or paint the inside of the pipe, that would be a capital cost as well, and that's to your advantage. But it degrades over the epoxy coating degrades after a period. Now, I'm not sure what would happen if you were to put a liner. You could put a liner into the pipe, like a polyethylene liner, pull it through and see what would happen. I'm not sure about that, whether it'd be worth some trying.
Yeah, sure.
Yeah.
Okay, thanks, Alan.
You're welcome. Some of these days I have to visit Phuket.
Anytime. After we pass this,
oh yes,
I need to visit Phuket too. I'm missing Phuket. It's 2 months
sure
already.
Yeah. Oh boy, I'm sure you do.
Alan, this is Marcelino. How are you doing?
I am good, thanks. I hope you got my email from the other evening.
Yeah, okay. I'm very confused because of coronavirus. As you may be aware, Brazil has been passing through a terrible moment when you talk about this disease.
I know.
Yeah.
Well, as I said, I pray for you fellas every night. 88,500 people dead. Not good.
Yeah, that's it. I think that's approximately 14,000 people deaths. Okay.
Oh, really?
Died. Yes.
Oh.
Yes. I'm talking 14,000. Yes. Okay.
That's awful.
Yes, but it's okay. My question is that there is a small group incubated at PUC,
Yes.
named Sinduti, and this group is a pipeline simulation group. And
Right.
what could be your suggestion to see this group more engaged with the international pipeline community? I know that is a local group, is a local people with a huge experience. How to suggest, how could be your recommendation to see this group more linked, more engaged with the international community? How to do that?
Well, I know that that's a passion for you, Marcelino, which is great. So what's their expertise? What area are they working in? A lot of different areas or one particular area?
Sorry, I think that Professor Luis Fernando could talk a little bit more about this,
right.
But it's a very competent group, and they have been developing simulation, gas pipelines, liquid pipelines, okay? But I think that Luis Fernando could talk a little bit more about that because he's the one of the managers of this group, okay?
Right. Well, let me ask, Petrobras are members of PRCI, right?
Yes, Petrobras is a member of PRCI.
Well, years and years ago, Marcelino, I struggled with those fellows because they only wanted to allocate their research money to companies in the United States. And I said to them, there's lots of other people, doing good work in other parts of the world. And it took a long time, including working with Monas or Scala, whom you know well, get them to spend money actually in Canada. And in fact, they awarded CFR a prize for the best research. And so I would say that's one way of trying to get, improve the group to improve their contacts, to try to lobby PRCI to give work to them. That would be one. And I do the same thing with AOPL or some of the bigger, groupings. You've got the more sharing that you have with groups, collaborative research, collaborative programs, looking for money from, say, even the European Union. So they could be looking to partner with Total or some of the big companies, Gas Uni, or some of the big companies in Europe, and go after joint funding. And they'd be pulling their research. And I know the European Union are very keen on doing work like that, America is very difficult, as you know, because they usually only think the world ends, at the American border, a lot of them.
May I talk a little bit about this? This is Mario Pezzi. One way of producing good projects at the PRCI, you should be very active in the commissions,
yes,
technical commissions, and also you should try to lead the project. So you can invite other institutions globally, right? And when I led a project, I could enlist University of Santa Catarina for
right,
evaluating the composite repairs, right? So in order to participate, you have to be active in offering your expertise and looking for projects that are important for your company.
right.
Thank you.
So with composites, I would urge you to talk to Chris Alexander. Do you know Chris? Do you know Chris Alexander?
Yes, I know from stress.
Well, yes, but he's left Strat and
Yeah.
he's working. He works for himself, but he works for his business. Really, is on innovation and putting companies together with other companies, and so worth your while checking. I can send you his contact. But that's what he's doing these days. He's using his expertise to bring companies and groups together. So you know, Chris would be a good guy to talk to. He's a very nice fellow, of course. So I can send you the details to Bruno, and then you can get it from Bruno. How's that?
That's a good idea.
Yeah, how to contact, because Chris left Stress International, SES, a few years ago.
And also for startups as well. Thank you.
Yeah, okay. Now you've got young pipeliners there, so where are their questions? To be a young pipeliner, have to be under 35.
I'm Hugo from PUC.
Right.
Engineer from Sindut. I'd like to know what's your perspective about the gas in the future. If we know we're passing through the coronavirus and the crisis in oil, so do you think there is a chance to increase the market share in gas and oil in the future with the renewable energies in this scenario?
Well, I think renewables, let's hope that they come. They'll come at some point, but you need to bridge between now and when the renewables. Even if renewables were fully functional, they would really only be able to supply 50%, 60% maximum of the world's energy supplies. We know that. So you've got to have a fuel that's clean burning. Natural gas fills that. And I think that's where the future will lie, where people will try to make more use of natural gas for producing electrical power, and then electrical power would be used for driving cars and so forth. What you will find in the next couple of months, though, is just like the oil futures went negative last month. It looks like the gas futures will go negative in the next little while because of the LNG issues in China, where the market sort of closed up a bit. But I'd say that natural gas is a huge. You can take a city like Sao Paulo and trying to reduce pollution. If you look at the health bill that is involved, I mean, no, people don't. But to keep people breathing clean air has got to be worth a lot of money. And windmills and solar power have their place, but it's going to take another 40 years before they ever become hugely important to the economy, So I think that natural gas still has a bright future. It's a low-cost fuel. And so if you can produce it at a low cost, actually right now, I mean, in the coming weeks, there'll be a huge problem because Qatar has been unable to sell its liquefied natural gas. It normally sells it to India and China, but because of the shutdown, it's got a glut of natural gas and it's going to probably depress prices, but that will be very short term. Does that answer your question, do you think?
Yeah, thank you.
Hello, Alan. How are you doing?
Yes, I'm good, thanks.
Yeah, it's great to hear you. I just loved your presentation. Thanks again for describing well these hydraulics pipelines. And I'm also from Sindut, from PUC, as Marcelin said, and we can talk later about our business.
Sure.
And my question is, you said a lot of slag flow. How is the importance of not having the slag flow inside of the pipeline, so your SCADA system can see well what's happening inside of the pipelines. So in this vision, I believe that one of the most important things that you have to got with that is to avoid leaking, the leakage. So in terms of illegal tapping that we have a lot of here in Brazil and in other places, can you say how you're dealing with the illegal tapping in Canada, and if you have the best practice that you have there, and maybe the best technology that you have experienced in Canada? Can you explain a bit about it?
Well, what they do in Canada is they buy the book Managing Pipeline Integrity, and they look up chapter 12 that Marcelino Gomez wrote on how to deal with vandalism and theft from pipelines. Have you seen that? Have you looked at the chapter that Marcelino wrote?
I have the book. I have the book right here.
Oh, there you go. No, I mean seriously. Well, theft is very minor by comparison. It's not that it doesn't happen, but it's not a big issue in Canada by comparison to other parts of the world. But losing product from the pipeline damages a company's reputation, because if they don't find that leak very quickly, it can do a lot of environmental damage. But even the very fact that they've reported any losses means that it's damaged their reputation, and that can cost them the ability to build more pipelines. So it means then that there's a big effort here in Canada to improve our ability for leak detection. Now, the physics would be that if you just use computational methods, you're limited to about 2% of the volumetric flow, right? If you use mass balance, it's not accurate enough. So you've got to use other systems, whether it's fiber optics or smart bulb technology, acoustics. There are 5 of them that are being investigated right now. They've reported on it at the Center of Frontier Engineering Research. Now, I can try to get you. I'm not familiar with where exactly they are, whether they publish their work or not. I think they might be, but I could get you a link to that or send it to Marcelino, because the industry is so concerned about it. They spend an awful lot of money doing prototype testing, and they've picked the best methods, the best 3 methods out of the 5 that they've tested, or they developed in the laboratory to take it to full scale. So not my area of expertise, but I know they're doing it, and I'll be happy to put you in touch with the group. But Mahir Nassim would be, or Mark Stevens actually is the chief engineer at CFR. If you write to Mark or contact Mark, I can get his details to you again through Bruno or Marcelino. But that's who I would write to, because they've been doing most of the work in Canada around leak detection. That's about the best I could do for you right now.
Okay, thank you very much, Alan.
So where are your young pipeliners? Where are they? Have they all gone home or gone to sleep?
I'm a young pipeliner. Bernardo, maybe you can do another one.
Yeah. Yes. Yeah. Let me do a question. I'm a bit afraid to do some technical question here, because there are a lot of experts in the audience. We have Sydney from PUC, Pires. I'm afraid to say something wrong here, because I passed it in his discipline.
Did you say Sydney? Is Sydney there?
Yeah, Sydney, can you hear us? I think he's here.
Oh, good to hear from you. Okay, carry on. Sorry, what was your question?
No, my question.
Yes, I'm here, Alan. Pleased to hear you.
My pleasure.
Yeah, Sydney is a young pipeline professional as well. Okay, yeah. And I think that Sydney could contribute with Bernardo. Okay,
I see Sydney's photograph here, and just because he's got white hair doesn't mean anything.
But
do you remember Sydney? Do you remember Sydney taking me out to CT Dut? Were you at the
Yes.
visit? You remember?
Yes, of
Oh,
course.
yeah, that's good. Well, now, so what was your friend had a question? What was his question? I wonder.
No, it's a quick one. Actually, if I want to change the fluid that I'm transporting, let's imagine that I'm on like a liquid or a gas line, and then I want to transport something completely different. I don't know, hydrogen or something. What
Sure.
would be the steps to do this and keep the same steel that I already have, if this is possible, of course?
Well, it depends. I mean, you'd be very ill advised to try to use convert it to moving hydrogen, because hydrogen is a very strange material. We did try that at TransCanada to see if we could transport hydrogen in our existing gas pipeline system now. But changing service, there are protocols for that. If you go, it's much easier to go from gas to liquids than to go from moving liquids to gas. A gas pipeline could be in service for a long time, and fatigue is not going to be an issue because there's no cyclical loading on it, no pressure cycles. In the little presentation I gave there, I mentioned that just the way you operate a liquids pipeline, you do get a lot of pressure cycling, so you can get fatigue cracking. So it means that when you're going to do a change of service, the first thing you have to ask yourself is, what is the current condition of my pipe, and how would I know it? So you probably have to run inline inspection tools and do some hydrostatic testing just to validate the condition of your pipe. And then when you start thinking about the physics of what it is you're trying to move, well, you can do that by looking at the material properties that you've got and whether, in fact, you could withstand the pressures that you might need. You might have to operate your pipeline at a higher pressure if you're moving gas, for example, to be economic. So there's a bunch of steps, but there's established methods for doing a change of service. It's in our Canadian standard, actually, what the protocols are. Z662, change of service. Mostly, though, it's to accommodate people who have been producing gas and that the gas is the reservoir has gone sour, so they start getting sulfur in their line. And that's a change of service. That's a big change. But changing, say, the operating fluid, the first thing you need to do is just, I think I have a paper on it somewhere I did. I know I did years ago, but I'll try and dig it out. But you do need to know the condition of your pipe. We did a TransCanada change, and you may even hear about it, the Keystone pipeline. The Keystone pipeline was was a very old gas line that was converted to 40-year-old gas pipeline, converted to moving oil. And well, it has leaked 4 times in 10 years. Right? The part that leaked was the brand new stuff that they built in the United States. The part that was built in Canada hasn't leaked at all, so it's good pipe. But you do need to know, seriously answer your question, you need to know, have the material test certificates for the steel of the pipe that you've got and know the condition of the pipe that you've got, so you can do some reasonable calculations with confidence about, the outcomes. But people do. Change of service, change the direction of flow sometimes. That would be another change of service that you could look at. I don't know if that answers your question or not.
No, yes. Thank you very much.
But there is a protocol for doing it, like different steps that you need to look at.
Yeah.
And it always starts with knowing the current condition of your pipe. And you put some degree of confidence in inline inspection, but not 100%, because you've got to do that plus hydro testing. Hydro testing will find the big defects and won't find the small ones. You have a better chance of finding the small ones with ILI.
Okay, thank you.
You're welcome.
Hello, this is Andrea from City Dut. Good evening, everybody. Alan, thanks a lot for your presentation.
You're welcome.
Very good indeed. As you mentioned, your CI, we are now CityDoot, we're now discussing with Monas and Cliff the
Yes.
development of GAIP on illegal tapping. So we are
on
starting
illegal
on-
tapping.
Yeah.
And you're doing that with Manes.
Yes, Monas, yes.
So what's you're looking at what maybe encroachment and using satellites or something like that to look at people working around your pipeline?
Yeah, in fact, a bit of all that. So we are now just discussing to try and close a bit the scope, because it goes from satellites to detection of signal from cell phones and
That's
all-
right. Yes. Yeah. No. I think actually I'm not sure. Manes had a scheme. I tried to help him. I'm supposedly his mentor. Can you believe? But he did discuss with me the whole business of cell phones and being able to track with cell phones. It's very interesting. He can do it. So I'm glad that you're going to try something like that. So that would be something that you fellas could do, where you would offer to run a pilot program, on a real pipeline for PRCI on that.
Yeah, that's the point. So the idea is to try and close a scope that we can make the experiment all at CityDoot.
Yes.
And combining solutions that could find over here, and in fact it would be not one single point, but also complementing different technologies to try and cover as much the need, looking at the work headaches of the operators. So on that, if you could, I could take the chance to ask you, and what you think that would be the worst headaches for operators at the moment on that subject.
In terms of people encroaching on their line?
Yes.
Well, I mean, you're maybe looking at it from the point of view of people thieving, but it's a big integrity issue in the United States. If you look at the primary cause of pipeline failures in the United States, it's third-party interference. It's mechanical damage. People coming, where they shouldn't be. So monitoring and the ability to remotely monitor people working or coming close to the pipeline is critical for them. So, I would think that PHMSA and PRCI would be pretty supportive of anything that would help them understand who's working close to the pipeline or coming close. I mean, not everybody's going to come close to the pipeline to steal from it, but even people building close to it, working close to it, other utilities, maybe, you want to know that they're about and improve your communications with them. And so satellite, I mean, I think I worked with Manes on that about 15 years ago with Visitless Integrity Assessment. That's what his company was called, VIII. Visitless Integrity Assessment, right?
Right, that's it, yes. So, I'm going to have a meeting with him tomorrow just to discuss a bit further and try to close it more, define the scope on that.
Yeah, you should. And by the way, Manes is one of the few people that was one of the early people that was able to get money from PRCI. Because I told you, see, PRCI is based in Houston. And Houston, they have what's called an old boys club. They have I'm British, so you know what an old boys club means. We all went to the same school, so we know each other, we trust each other. And they do that in Houston. And they do that in Tulsa. But sometimes they think that nobody else can have a good idea but them. And they're stupid in thinking that, They're clever people, but they can be stupid because they think they're the only people who can think of good ideas. And so it took a while before we were able to convince PRCI to let work out. And Manes was one of the guys that did get work from PRCI, so he knows how it works. He knows how it works very well.
Great. I know what you mean. Good to hear that. Thanks a lot.
You're welcome. And enjoy your conversation tomorrow with Manes.
Okay, I'll do. Thank you.
getting late with you fellows.
Okay, Alan. Oh, here's Marcelo Renault. Nice to talk with you. Very good to listen your words.
How are you?
Marcelo Renault. Oh, Alan, is a question a little different from hydraulics. So would like to see some words from you about public perception, looking for future installations, gas pipelines and liquid pipelines installations. What you can say for us considering public perceptions and the possibility and the ability that the industry has to achieve licensing? What you can,
well,
what you,
you know, it's become very difficult, especially in Canada, Marcelo, to get approval for new pipelines. People, people don't understand that their homes have to be heated. That if they look around their home and they find the amount of plastics and so forth, it had to come from somewhere. But they're in denial, and they think, well, I don't know, we shouldn't have any more pipelines. We shouldn't have this. It's become very difficult, and in terms of, I think the industry has to demonstrate its benefit. You know, a long time ago, people worried about nuclear power, and they were worried that people, with nuclear power, it was dangerous. And so the nuclear industry went about trying to change the public's perception of that. And they looked at the benefits of nuclear stuff, nuclear medicine, people being treated for cancer, airports where they were examining your baggage by having x-rays which are nuclear related. They sold the positive things about what they were trying to do rather than worry about the negative stuff. And I think that's what we have to do as a pipeline industry. We have to tell people, well, look, this morning, for example, the Association of Oil Pipeline, well, you're looking well. I can see your picture now. You're looking well. If you look at the result, the publication this morning from API and AOPL, they're showing that there's been a 35% increase in the amount of pipelines built in the United States, and the amount of incidents has dropped dramatically. So pipelines are safer than they've ever been. And the public need to know that, because I think they're frightened. Right? If you look at where, if you're going to be building a pipeline in a part of the country where people have never had pipelines before, then they worry about that. You know what I mean? Like, they're concerned because they're concerned about what they don't know. And they've heard stories and they worry. But I think when you start looking, the best thing that you can do is show them your record and how you've behaved as a responsible pipeline operator, and why wouldn't they trust you? Can you hear me?
Renault, you are muted.
Yes. Okay.
No, okay.
No,
So,
I'm listening very well. Okay. I think that in the last Rio Pipeline conference, we talked. We realized that it's important to talk, to have reference for people that is not engaged specifically in pipelines. So to show the business, to show the practice for people that are not specifically technical in this business, no?
Yeah.
Because we talk among us, no? All the time.
Well, we try to explain to people that you have to heat your home, you have to drive vehicles. Where does that come from? And even if you use an electrical power like Tesla, they need to get electrical power. It's not all going to come from solar panels. It has to come from elsewhere. So, but a lot of the people who, the problem is, a lot of the people who oppose these pipelines, it doesn't matter what you say, they will never be convinced. Can you hear me? Is my microphone still working, or?
Your microphone is working, Al. I think that it's Renault connection that might be oscillating.
Okay. Well, do you know what I mean? It's you have a lot of people who oppose any form of development. It's not. We used to have an acronym in English. It was called NIMBY, NIMBY. And what that means is you can build something, but not in my backyard. That's what NIMBY meant. So I don't oppose you building it, just don't build it near me. But now what happens is we have people, and they're not NIMBY, they're banana. And banana stands for build absolutely nothing anywhere near anyone. And that's dangerous, because that means that we would never progress as a society if we did that, you know? So you have to watch who these people are that oppose, because you have to ask them, well, what is your alternative and when will it be available? And if they say, well, it's going to be renewable energy, you say, well, when will you have that and how much? And when, how, you know.
Okay, Alan, but I'd like to talk a little bit more about this, because Marcel is out and I had the opportunity to talk with him, and yes, we have the same idea and the same vision that we have to change the public perception about our business.
Right.
I believe that we have to invite other communities to attend our events, or yes, to organize a specific one to convince and to show and to present our arguments about our business, about our industry.
Yeah.
I have no doubt that we have to invite these groups and to explain about yes, our business, because yes, I have been talking with Alan Murray. Alan Murray has been talking with Cliff Johnson. Cliff Johnson has been talking with Phil Hopkins. Phil Hopkins yes, has been talking with Bill Bird. Okay, yes, Bill Bird. Bill Bird will talk with Patrick Weiss. The same group, the same family, the same community.
No, you have to invite these people to your. Actually, before I gave this presentation, I was joining in on the advisory group for our young pipeliners, and the chairman gave a little talk, and she said that she had presented at a conference, and a lot of people walked into the conference and started to not physically attack her, verbally attack her, and they were opposed to pipelines. And she said, well, okay, why don't you tell me what your problem is? Because your problems, it turns out, are my problems. I'm worried about the future. I'm worried about climate change. I'm worried about the environmental damage. I'm worried about creating work for people and so forth. But you have to bring them in. Like if you leave them, and so at our workshops that we have in Banff, Marcelino, we've invited people to come. We've invited the non-governmental organizations to come and speak and share their points of view and listen to what we have to say as well. And it's been very good. But you're right, you can't have the same people talking to each other. It's got to be fresh voices. And are these people willing to come and share? You know, so it's the law of reciprocity. You have to invite them to come, not just to listen, but perhaps to speak and say, what are your issues? And let's hear what you think, and we'll share with you what we know. That's what I would do. That's what we have done actually at our Banff workshop, you know. We invite them to come. Now, we don't invite the newspaper people because they only want sensational stories. They're not interested in.
Yeah, but I think, Alan, I think that we have to organize seminars and events in New York, London, Rio, Sydney, okay, just to spread our vision and our perception about our business. It's just a general comment.
Yes.
But another one is that last week I was talking with Bill Bird about the IPC, because yes, Bill Bird is the present chair of the International Pipeline Conference.
That's
and,
right.
I'd like to receive from you some update about the possibility to cancel or to postpone IPC 2020 because of the coronavirus or something like that. What is your vision? What is your perception about that?
Well, right now, well, two things. First of all, the papers are being, today was the cutoff for reviews of the papers. They're still going to publish the papers, print the papers, whether they're actually send it or not. The ASME has said they'll print papers. So they have these papers. What they've been doing is trying to work an alternative plan in case they're not able to hold a physical conference, to look at whether they could do it over the internet. Not, what would that look like? So they haven't decided to cancel the conference yet. They were waiting on medical advice about that. And they're looking to see if, you see, in March, as you probably, well, you do know, because weren't you part of that conversation in Berlin at PTC?
Yes, yes.
Well, the problem at PTC, because we're having the same issue with another workshop here, which is not until next April, but we thought we'd make a plan. And I wrote to Phil and I asked him what happened at PTC. And he said, well, unfortunately, they had to change the plans very, very quickly at the end. And, they would have done things differently if they'd had more time. So Bill has had a working group. There are 5 or 6 of us on that working group to see how you could hold a virtual conference and what that would look like. But certainly for the papers, they're going to go ahead with accepting papers and printing them. And they haven't made a decision yet about postponing the conference. But they'll have to do it pretty soon because they have commitments at hotels. They've got, things like that, people traveling. What he did do was, part of that exercise was contacting senior people in the industry to find out would they be sending people to the conference if it was to be held at the end of September. And one of the senior people told him that he was very doubtful because it looked like they were going to have to lay 30% of their staff off. So there's a lot of considerations here about whether, in fact, even if they held the conference, would people feel comfortable coming? Would companies spend the money to send them? Or would it be better done over the internet, So I don't know whether that helps you or not. But no, Bill's still working on it. I talked to him yesterday, actually, and they're still going ahead as of yesterday.
Okay, thank you. Yes, it's a big, big mess. It's a big, big problem. It's a big, big challenge.
For sure.
Okay, Alan.
Sorry?
I'm not sure it's now, but once again, nice to see you. Thank you very much for your...
Welcome. We probably should end it, right? Because I'm sure you're getting tired.
Yeah, I would thank you again, Alan, for staying with us up to now. It was really nice. It was a pleasure. Thank you for having your time to talk with the young professionals and the senior ones. I mean, that's why YPP exists, to try to make this bridge, right? So thank you very much for this again. Thank you for Danny, for ASME, PSD Division. Thanks
Bernardo.
Yeah.
Yeah,
Thanks.
sorry for interrupting you, but I had one final question for Alan, if that's okay.
Yeah, go ahead.
Yes.
Yeah. So Alan, my name is Raissa. I work with Bernardo and Bruno in the Young Pipeline Professionals Association. And so thanks a lot for the presentation. This was an amazing overview. My question would be more inspirational than technical, if that's okay.
Sure.
Considering your exceptional history in the pipeline industry and all the lessons that you have learned throughout the years, I would like to ask you something like, if we had all the young pipeliners watching us right now, which message would you like to send them? Would you like to send to us?
Well, I think the most important thing is your reputation. As an industry, we have to protect our reputation. We have to do the right thing, and then people will trust us. And you have to do your part with that, and that means that you have to be seen to be trustworthy. And so the best thing for young pipeliners, I think, is to just be aware of their personal integrity. Don't let anybody get in the way of diminishing that in any way, because it takes a long time to build a reputation and you can lose it very quickly. So I think that the young pipeliners are going to make a big difference because they're very keen, they're very enthusiastic, and they want to change things, and that's important. So that would be my message to them. And you guys it's great that Danny was able to report the successes that you've had. And you've got Tom Butnick to look forward to, and he'll have more than 2 days to prepare one. But he'll give you a good talk, that's for sure. So it'll be good. And thanks for being patient with me.
This was perfect. Thanks a lot, Alan.
Take care. Take care.
Thank you.
Stay safe, everybody.
Thanks a lot again, Alan. It was a pleasure. It was a lesson about hydraulics. Thanks again very much.
All right. Take care. Have a good night.
Thank you, Alan.
Thank you.
Okay,
Bye,
guys.
Alan.
Thank
Bye-bye.
you all. Bye.
Thank you.
Bye, Alan. Bye, Alan.
Take care.
Bye.
Bye-bye. Nice seeing you.
Thank you.
Thank you.
Aí, tenho 2 minutos para falar, hein?
Por quê?
Meu jantar chegou, graças a Deus.
O que vocês pediram?
Ah, uma coisa bem light, uma saladinha. Te mando uma foto depois.
Imagino que deve ser bem light mesmo.
Cadê Bruno? Foi embora? Abandonou?
Ele mandou alguma coisa aí? Eu não vi se ele mandou falando se ia voltar.
Vê se você tem que aceitar ele.
Tem não. Não tá no lobby, não. Ele mandou no zap aí. Eu só saí rapidinho aqui do céu.
Tá dando chabu.
Que aí até ver com o Bruno como tá a confirmação da galera da semana.
Calma aí que a gente tem um guest aí.
Removi o cano. Ai,
Ele é fofo, né?
é.
Fofinho.
Cara, não sei se faz sentido ou não a gente mandar a apresentação para ele, tá ligado? Tipo, pô, Alan, não deu tempo de fazer, mas fica aí para você ver também um pouco do que foi feito e tal.
Pode ser.
Porque acaba que a maioria da galera que participou era brasileiro mesmo, né? Então, de repente é legal mandar para ele, pedir pro Bruno mandar. Ele pega, manda para ele e pro Dani, né? Tipo, agradecendo. Faz um meio de campo aí com essa galera que precisa. E aí?
E aí? Ai,
O que
caralho,
que
tô
você acha
cansado.
de mandar a apresentação, a que a gente não fez?
Você tá gravando ainda, filho?
Ô, caralho, vocês têm que me lembrar de parar de gravar, cara. Eu não lembro.